Welcome back. Okay, let's just dive right into this explainer, which is specifically tailored to help you absolutely crush your upcoming exam. This is video 3 of the Mathematics series, and today we're focusing squarely on lines and planes. Specifically, we're looking at their intersections and the exact distances between them. We're going to take those abstract numbers from your textbook and translate them into a crystal clear understanding of three-dimensional space. We want to make sure you have the exact tools you need to ace this section of your linear algebra test. But before we look at the numbers, consider this real-world engineering problem. Imagine you need to figure out where a load beam perfectly intersects a plane, or you have to calculate the exact shortest geometric distance from a critical load point directly to a structural wall. In the world of structural engineering, close enough absolutely does not cut it. A miscalculation of even a few centimeters can lead to a catastrophic distribution of weight and ultimately structural failure. You literally need absolute mathematical precision to guarantee safety. So here is our roadmap for today. 1. Geometry in the real world. 2. Equations for lines and planes. 3. The Hesse normal form. 4. Calculating point-to-plane distances. 5. A worked example on the Lotfuspunkt. And finally, 6. An exam recap. Let's kick things off with Section 1. Geometry in the real world. To ensure safe structural design, you absolutely must know how to precisely model vector geometry in three-dimensional space. The vectors we're about to calculate, they aren't just arbitrary lines drawn on graph paper. They represent actual physical forces and immovable directional boundaries in engineering. Think about it. When an architect designs a cantilevered balcony, the safety of that structure depends entirely on calculating exact stress points and clearance tolerances. That physical reality is exactly what vector intersection and distance formulas allow us to map out with perfect fidelity. Moving right along to Section 2, Equations for Lines and Planes. Let's break down the foundational toolkit you're going to need to describe these shapes mathematically. Notice the stark difference here in how we define a line versus how we define a plane. Lines are easily built in what we call parametric form. The equation is x equals p plus lambda times r. What does that actually mean? Well, you basically start with an anchor point, right? That's your vector p. And from that specific point in space, you stretch out along a directional vector, r. The parameter lambda is simply a scalar, a multiplier that dictates exactly how far you travel along that specific direction. It's a highly additive, step-by-step way to construct a straight path. Planes, however, operate on a totally different logic. They're elegantly defined by an implicit form, written as the inner product or dot product of vector x and vector n equal to d. Instead of building the plane point by point with scalars, we define the entire infinite surface by what it is strictly perpendicular to. That vector n is the normal vector. Think of it like a pole sticking straight up, locked at a perfect 90-degree angle to the flat surface of the plane. The dot product captures the relationship between any point x on the plane and that perpendicular normal vector, setting their interaction equal to a constant d. Understanding this fundamental difference between building a path and defining a surface boundary is absolutely key to mastering vector geometry. All right, let's look at Section 3, the Hesse normal form. This is your secret weapon. The crucial point here is that you must normalize the normal vector before you attempt to calculate any distances. Listen to me carefully. If you just use the standard implicit form we just discussed, your exam answer will be spectacularly wrong. The Hesse normal form requires your normal vector, denoted as n0, to be strictly normalized. Mathematically, this just means scaling the vector down or up until it has a magnitude or length of exactly 1. You achieve this by taking your original normal vector and dividing it by its own mathematical length. Why do we bother doing this? Because by forcing the vector to have a length of exactly 1, it functions as a pure directional indicator. It strips away the arbitrary scale of the original vector, guaranteeing that the math won't artificially stretch or shrink the distance you're trying to calculate. In fact, your professor's lecture notes contain a critical warning regarding this exact concept. The notes explicitly state that the distance formulas only work for an n0 vector with a length of exactly 1. When you divide that original normal equation by the magnitude of the normal vector, a really fascinating mathematical shift happens. The arbitrary constant d on the right side of the equation magically transforms into d0. That d0 is no longer just a random algebraic constant. It directly represents the exact true geometric distance from the coordinate origin point perfectly straight down to the plane. Now for Section 4, calculating point-to-plane distances. Let's see how this all builds into an unbreakable 3-step methodology for your exam. Step 1, you find the normal vector of the plane. If the plane is given to you in parametric form with two directional vectors, you'll typically find this normal vector by calculating the cross product of those two directions. Step 2, and this is where most students fail, so pay attention. You normalize that vector. You calculate the length of your new normal vector, and you divide the vector by that exact length. Step 3, you compute the distance. You simply plug the coordinates of your arbitrary point directly into the x variable of your newly created Hesse normal form equation. Seriously, signpost these 3 steps in your brain right now, because following this exact sequence is going to save you from making careless, grade-tanking errors under exam pressure. Okay, time for section 5, a worked example, the Lot-Fußpunkt. The concept of the Lot-Fußpunkt beautifully describes the foot of the perpendicular. Imagine you're holding a perfectly weighted plumb line from a specific point high up in the sky, and you let it drop directly down onto a slanted roof below. The string falls completely straight, perfectly perpendicular to gravity. The exact singular intersection point where that string hits the surface of the roof, representing the absolute minimum distance between your hand and the plane, is your Lot-Fußpunkt. We are going to find that exact distance mathematically right now. Let's step through the calculation deliberately, using the actual numbers from your notes. We want to find the exact distance from a floating point Q, which sits at coordinates 1, 0, 7, to a specific geometric plane E. We start with step 1, finding the normal vector. We calculate the cross product of the plane's two given direction vectors, which are 3, 0, 1, and 1, 2, negative 1. Executing that cross product generates our normal vector, which comes out to negative 2, 4, 6. Now we need the length of that vector. We find its magnitude by taking each component, squaring it, adding them together, and taking the square root of that entire sum. So negative 2 squared is 4, 4 squared is 16, and 6 squared is 36. 4 plus 16 plus 36 yields a magnitude of the square root of 56. And we can mathematically simplify the square root of 56 down to 2 times the square root of 14. Once we have that magnitude mathematically confirmed as 2 times the square root of 14, our absolutely crucial next step is normalization. We build our Hess normal form by taking the plane equation and dividing it entirely by that magnitude. This scales our normal vector down to a pure unit of 1. Finally, we arrive at step 3. We take our point Q, the coordinates 1, 0, 7, and we plug those values directly into the x vector spot in our new normalized equation. Because the vector is purely directional now, the math effortlessly simplifies down. The dot product is calculated, the absolute value is taken to ensure a positive distance, and we compute the final exact shortest distance from the point to the plane as exactly 4 over the square root of 14. Boom, you've got it. Let's wrap this up with section 6, our exam recap. Screenshot this slide right now, burn these 4 concepts into your memory because they are the foundational pillars of your upcoming linear algebra exam. You must know that a line is built directionally and relies on a parameter lambda to determine length. You must understand that a plane is defined implicitly by what sits perpendicular to it. You must always remember that normalizing a vector means dividing it by its own magnitude to create a unit length of 1. And finally, you have to internalize that the Hesse normal form is the one and only acceptable way you can accurately determine distances to a plane without distorting the final geometric reality. Remember, this isn't just arbitrary math designed to make your semester difficult. This is exactly how engineers guarantee that bridges bear weight correctly and buildings don't collapse. This geometry is the fundamental language of physical reality, helping us map out safe parameters and tolerances for everything from microscopic automotive parts to towering skyscrapers. You now know exactly how to find the perfect distance to a flat plane. But here's something to ponder as you prepare for your next lecture. What happens to your structural models when that wall is completely curved? Or when the physical load shifts dynamically under severe environmental stress? How does the math adapt then? Well, we're going to leave that complex geometry for the next explainer. Keep practicing your normalization and good luck on your Mathematic I exam.